the next talk is going to be a number of demos from, I think, Ampia, from HPE, and from 9 Elements. And Ron might also be demoing something as well. So stick around for that. It's going to be in a minute.
Yeah. Exhausting, huh? Whoops, you're muted. No, you're not muted. Are you muted? I don't know. Yeah, whatever. Huh. My video is not working.
All right, so we'll have to make sure everyone has joined. So I think it was, so I think we'll need Christian, Walter, Jean-Marie, and
yeah, GM joined.
as well.
Yeah. Mm-hmm.
Yeah, it looks like everyone's here. All right, go ahead, Ron.
Oh, I go first? Right?
It is okay.
Hello?
Sure. I don't know if we have a real schedule for this. So if you want to go first.
I was going to volunteer to go last because I did. I actually showed kind of one of these systems, and I thought it only fair to let you all have enough time for your demos. So if anyone is ready to do a demo, I think I should be the last person because I've had a little demo time already.
I can try to make a demo if you want.
Huh?
I can try to make a demo if you want.
Yeah.
If it works, hopefully.
Where are you right now, Jean-Marie?
I'm in Florida right now.
I thought you were coming to California.
I was in California up to last Saturday, so I flew in during the weekend.
Okay. Oh well. So you're doing your demo. You can share your screen, and away we go.
Let me try to see if it works. Sure. Oops.
Yeah, looks good.
Okay, so let's try to run the demo during 15 minutes. So I'll be demonstrating you open source firmware on top of a DL360 Gen 10 from HPE. I'm using our CI infrastructures, which is used to develop open source firmware at HPE. The first thing is to start an interactive session. Why it is processing that? So I just wanted to mention that everything is open source. So the CI code is available on GitHub, Hewlett-Packard OSF CI. And during that demo, I'm going to use the OpenBMC repo, which is also hosted by Hewlett-Packard, and the Linux boot repo, the main bound part, which does support the DL360 Gen 10. So we are going to recompile during this demo OpenBMC and Linux boot. We are going to execute that on the ProLiant. And if I'm lucky, I can SSH directly to the Linux boot environment and boot Ubuntu 20.04. I must mention that I got a bug up to about 1 hour ago. So I hope everything is set up properly. The input of the CI is a GitHub, that is a GitHub repo. So I can mention my own OpenBMC fork of the Hewlett-Packard OpenBMC and a branch and launch a build. So this is just going to execute OpenBMC build on compiled systems. And I can see the output happening there. So in parallel, I can do the same thing with Linux boot. So this is taking as an input a GitHub repo and a branch. and I can launch a build. So we can have in parallel both builds running. They probably are going to last for about 5 minutes. So if you have any questions during that time, so feel free to ask me questions. The backends that we are using is a 128 core systems just to recompile everything. And I'm caching most of the content, so which explains why OpenBMC build is so fast. So if you have a very specific OpenBMC branch or repo, this is going to take more time on that CI. What else could I add during that process? The Linux boot I'm using is based on the standard U root. It does include all of these commands. So not all of them, but I'm using the LV shell, and it's running quite straightforward. So to support the SSH, I made a very bad patch, which is to untar the CPIO archive. It's not an untar. It's
CPIO.
Yeah, that's a CPIO archive trick. So I'm untarring it, or I'm opening it up and pushing some SSH keys directly into it and repack it. And then I'm using that as an init method stuff. So my goal is to try to avoid to do that and just doing it directly straightforward inside uroot. But for this demo, I didn't have enough time just to implement everything. So the kernel is currently compiling. I think the OpenBMC stuff is, yeah, it's going pretty fast. So it's remaining only 7 tasks. It's currently building the image. What you can see here is the remove aspect. So we have a lot of Dixie inside HPE BIOS image. So more than 600. So I'm removing about a little bit less than 200 Dixies. So there are the very high level ones. What we are trying to do to support properly open source firmware on Linux boot with Linux boot is to have a UEFI implementation, which is a shrink down version of what we have today. The team is working on that, and we are expecting to have something which works properly in Q1 2021. So everything is done. That's great. At least the build worked. So the next step is to load the firmware. So when I'm pressing that button, this is going to load the firmware on the flash emulator, which is directly connected to a physical server. So I can load the BMC and I can load the system BIOS firmware. So this is going to load the last build. The image in that case is 64 meg. And this is going to work, I think, which is great. Then I can connect the power. When I'm going to connect the power, this is just going to feed the power inside the server. And we can see here on the serial console coming up from the GXP ASIC, which is our BMC. That's a specific ASIC from HPE. You can see it as a competitor of SPID or Nuvoto. That's a proprietary implementation. We do have 384 meg of RAM. So depending on the version, it might be a little bit bigger or smaller. That's a single core ARM processor right now. So we are working at improving that. So OpenBMC is currently booting. This is going to take a few minutes. The key things with OpenBMC implementation on that platform is that the SPI bus for the system BIOS is not connected to the PCH on HPE server. It's directly connected to the ILO chip. So, and the ILO chip is providing the SPI image to the PCH when we turn on the host. So in OpenBMC to do that, we made the choice to replicate the content of the system BIOS image in memory. So roughly that's why also the boot time is a little bit longer. So we are reading the whole SPI image and put that into memory and serve it to the PCH. One of the key advantage in development mode is if you have to update the system BIOS, this is just a memory copy instead of reflashing the SPI image. And we think that from a security perspective, we can do some funny things like signatures and a few enhancements. So I think it is going to start sooner than later. I don't know if you have any questions right now. or did everybody fall asleep?
No, we are awake, Jim.
Okay. I think it is going to be ready in a few seconds. So this is the standard OpenBMC versions. It does include just the specific firmware from not firmware, but drivers from HPE. It is released under open source, so if you go on our GitHub, you can get access to everything. The only one thing which is proprietary is we have a binary blob. I know the community dislikes that. We are thinking about what we are going to do about it, but this is like the MRC code from Intel, but for our ARM processor. So this is the very, very low level initialization of the chip, which is still a binary blob. So I'm sorry about that. I think we didn't release it, not because of IP issues. It's probably because we thought it is currently useless for that generation of platform. But we can discuss about releasing more things. So OpenBMC is up and running. As you can see, there is a BMC web button which appears. So I can get there, and this is the OpenBMC web interface. So we can connect to the OpenBMC web interface. I'm doing everything remotely from Miami currently, and the server is in Houston. And I can go to the serial overland console. The server is up, and we have to wait for the initialization to come up. So normally, here we go. This is Linux boot kernel, which is booting up. Hopefully it won't crash. Okay, it's up. So I can run the DHC client. I'm very old school guy, so you will discover that. So this is using IPv4, and this is going to use SSH. It's not using yet Plan 9, anything related to that yet. But at least
we'll get you there.
At least it works. So hopefully, why I didn't get any IP address. Should be able to get that. Okay, there we go. I got an IP address. Can go into the SSHD configuration and run SSHD. And now let's get there. What is the IP address? Where is it? That's 1.10. Okay. Let's try to do that. It's complaining that. Can you still see my screen and the SSH?
Yeah.
Okay.
Yes. Yeah, we saw your password.
Okay. No,
all right.
There's no password. This is using SSH key exchange.
This is wonderful.
I am connected to my server using an SSH, and I can try to boot now. Let's try to see if everything works. Yeah, I got Ubuntu entry, and I can try to boot Ubuntu. So this is going to exec the Ubuntu kernel, and let's get back to the console, and we can see Ubuntu coming up. Using the CI, you can also test various operating systems, installer and reboot, and doing everything attached to that. So I got more and more, I shouldn't say customers, but people who are using that technology to develop OpenBMC and Linux boot image on HPE hardware. And what I could add is, so Jeff Krantz is going to be there during I think the panel by the end of the day. So, but he will be updating you more about our current plan regarding open source firmware. But we do have private offering which are ramping up for 2021. So we do have initial customers who are getting this hardware running open source firmware, and we are working jointly with them just to make it work and, let's say, production ready in 2021. So Ubuntu is started, it's working, everything is set up, and this is my demo. And in 15 minutes, that's great, it worked. Thank you. I don't know if you have any question.
That was, when you talk about the firmware, do you think you'll meet the goals of the March 2021 thing where it'll be redistributed?
We're working pretty hard to meet that goal. We think we could make it. The only one challenge is we won't be having a public offering in 2021. We will have only a private offering. So, but it doesn't mean that our customer couldn't get access to hardware. but we do prefer to have a private offering. The main difference between private and public is that we are raising the bar regarding the customer technical knowledge about open source firmware. So because we think it's a breakthrough technology, and this is quite disruptive. And we would like to have specific support for the customers and being sure that they understand the challenge that they might be facing or the benefit they could get from it. So right now, for example, to be part of our private offering, we just want to be sure that the customers is able to recompile by themselves OpenBMC and Linux boot. It could look like crazy, but we do have some customers who are demanding open source firmware from us, but fully integrated. So which means that we deliver them a curated OpenBMC image and a curated Linux boot image. We are not ready to do that. What we are ready to do is to enable the support of open source firmware on our platform, so we can prove that it can work. And we are upstreaming our patches to the various GitHub repo, the public repo. But we do not have a specific distro that we can support with our support team right now in 2021. And we just want to ramp up with specific customers. But we are pretty open to any opportunity to work together with people who are early adopter of open source firmware. Just to get back on the market demand and from the previous talk, I think there is a huge market demand. This is just a matter of organizing it properly and getting the right product into the field. And that's it. So there is still a lot of work ahead, and we are trying to automatize as many things as we can just to avoid that the investment gets crazy. And that's also why we're investing into that CI. So I'm going to interface that with the contest work from Facebook just to automatize testing also. And regarding the transfer of ownership, so we are currently following a path to build up chain of trust just to implement transfer of ownership, because we are facing the same challenge than everybody else into the market. So we do have a fuse into our ASIC, and this is just lowering the different capability that we can enable transfer of ownership. So, and the chain of trust approach seems to be a reasonable way to build up a transfer of ownership solution.
Okay. Sorry if I ran that over, but that was a really good answer. Back to you, Ryan, our next person.
GM, thanks. Great demo.
All right, so should we go with Ampere now?
Yeah, I can start.
That'd be awesome.
Are you able to share your own slides, or should we share the slides for you?
I can share the slides. I have them here. So is it coming up? Are you able to see?
Almost.
Oh, yeah, we can see. Thank you so much. All right, go ahead.
Hi, everyone. My name is Vanshi Zarkonda. I work at Ampere Computing. For those of you who may not know, Ampere Computing is a relatively new company in the semiconductor space. We recently celebrated our 30th anniversary. So Ampere wants to deliver products with high performance, power efficiency, and better total cost of ownership for cloud and edge servers. Today, I'm here to demo Linux boot on one of our Ampere platforms. Ampere understands the importance of the open system firmware project, and I'm here to demo Linux boot. That's one of the projects. That's part of the umbrella. And I'm going to try and demo a boot of Linux boot to the uroot shell, and then use uroot shell to actually launch a CentOS kernel that's already installed on the platform on an NVMe disk in the system. So I'm going to be doing a demo on our Ampere Ultra platform. Ampere Ultra is an SoC with 80 ARM64 cores, and it's trying to deliver predictable performance, high scalability, and power efficiency for cloud data center deployments. So let me switch over to my shell. Let me know if this is too small, but it should be visible.
I think it's okay.
So, okay, so I'm going to restart the server just to make it boot again. And the platform that I'm using to demo is called the Mount Jade platform. And I just restarted it using IPMI through BMC. And on top, you can see this is the CDL for the machine that should eventually start changing once the server starts booting up. And the system that I'm using has 160 cores because it's 2-socket, and all the cores are capable of running at 3 gigahertz. It has 512 gigabytes of DRAM that's capable of ECC. It has 1 NVMe SSD and 2 network cards on it, one of them being an Intel and the other one being a Mellanox card. The spec that's important for this demo is that there's a 32-bit megabyte SPI flash on there, and that's where the firmware for the ARM64 core is contained. So the the firmware image actually consists of ARM trusted firmware, UEFI, and Linux boot. And ARM trusted firmware is the starting point for runtime firmware on the ARM CPUs, responsible for initializing CPU, DDR, platform, etc. ATF will then load the UEFI and Linux boot image into memory and hand off to UEFI from there. Our UEFI implementation is based on Tiano Core /EDK2. It's available on GitHub now. So one of the things we tried to do with our EDK2 build is to, especially for Linux boot, is to just minimize the number of UEFI components that are part of the image. And then the only components that remain are the components needed for memory map setup, PCIe and PCIe setup, ACPI tables, SMBIOS, things like that. Our Linux boot image is built into the region that would be traditionally used by the UEFI shell. So we're replacing the UEFI shell with the Linux boot image. And the Ampere EDK2 platform's fork actually contains a Linux boot target. You can actually use the repo to build it. So you can see here now the platform's booting Linux boot kernel that's part of the Flash image and it's come up to the uroot shell. So earlier in the day, Ron actually gave a pretty good introduction to the mainboards repo, which was our starting point. And there's an entry for that here. And this is what I used to get started. This has this config, I'm not using it exactly as is. I made certain modifications. I changed things like I removed some utilities in there or removed some of the drivers. For example, the one on GitHub actually has IOMMU enabled and has a Marvel SATA controller enabled. I don't have that on this system. So in order to minimize the UEFI or the Linux boot on SPI Flash, I just removed them. Because I don't need them. So in terms of uroot, this is, it has a number of utilities that are built in Go, and everything is combined into a single image using the BusyBox mode. So you can see there's a number of things that are built into the Flash. And you can see that all the 160 cores are actually active.
It's hard to get used to.
Yeah, no, it's firmware and you have 160 cores enabled.
Yeah,
it's like, do we really need that? But nice to have. And then you can see, you can use a standard PCIe command. It'll show you what are the PCI devices. Like I have a Mellanox card here. I have the Intel NIC. I have the Samsung NVMe drive here. Let me actually close this.
hey, it's easy to update the database so you'll get real names for the OneDef and EOE if you want.
Sure, yeah.
Let me know if you want.
Actually, yeah, my image is a little out of date. I didn't rebuild the latest stuff. It's a little out of date.
But still, well, we're happy to do that when you want it.
Like I can even do IPMI dump to see some status of the chassis and DMI decode to dump the system information. You can see it says it's manufactured by Ampere. The product name is Mount Jade. And the serial number is just something that we've put in there. And I'm going to use DH client to actually get an IP address. I can use history. And it's going to send out an IP DHCP request, as we saw. Sometimes it works, takes longer sometimes. Taking longer than I expected. Well, in the meanwhile, so I wanted to bring up the make file that's used in the GitHub repo. The target that I'm using is Flash kernel. It contains all the uroot commands, and then the things I added is like ACPI related things and the DMID code and the IPMI dump. It's pretty easy with extending these. You can just add other commands as you need them.
Okay. And notice the OR equal ARM64, that gets you the ARM target. That's all you got to do.
Yeah. And it works without it. It's like I don't have to change anything. I just took the makefile, built it, and it pretty much works. As long as you have the right kernel config, it works. There's nothing that's ARM64 special, right? It's like I don't have to make any changes. Things just work out of the box. And now that I have an IP address, I'm actually going to get a boot script. It's just a shell script that I wrote for demo purpose. So you can see I'm just using the boot script. I'm going to mount the partition in the NVMe drive, load it up, and then I'm actually going to unzip the zipped kernel or the compressed kernel, because ARM64, you actually need to uncompress the kernel before you try to kexec to it. Yeah. And then you just kexec to it. And the nice thing is you have gzip built into uroot, so you can just boot a compressed kernel regardless, and you even have security. You have to actually make it.
I do want to mention, just to make sure it's clear, that all the commands you're running here that I've seen have been the written in Go commands from uroot.
Yeah, standard stuff that's probably just working on x86. I don't have to, again, no changes, right?
Yeah. The other thing I really neat here, I like the idea that we did this on the supercomputers, actually. The idea is that your boot script you pull down, right? It's not built in, and that way it's trivially changeable. I mean, I think that's a good model. I don't know how far you'll get, but it's a really good model.
Yeah, you can repurpose the server at any point as soon as it reboots, and you can tell it what it needs to do. You don't have to build anything in it.
This is nice.
So that's all I had for the demo. So some additional information. All the stuff is up on GitHub now. This is a little change from the slides I sent you on earlier. We do actually have the EDK2 code up now. You can go look at it. Actually, I can share the repo. Yeah, so we actually have a Linux boot specific DSC and FBF file as part of the EDK2 sources. You can just use that to build it.
So, is there any blob in here at all?
Sorry?
Is there a blob of any kind in here at all?
Yeah, to build the final image, which is the ATF plus EDK2 plus Linux boot, ATF is the only binary blob in there right now. To get the blob, you'd still have to contact Ampere. We're still working on a strategy on how to do the distribution for that.
Okay, and so sorry, with ATF you mean the ARM trusted firmware, right? So
yes.
So, but probably you're going to upstream it later on, or if you decide which way to go. Okay.
Yeah, we're still figuring that out.
Yeah. This is really, it seems to me that you're extraordinarily close to meeting the OSF criteria. Did I get that right?
We still have to figure out that part. Is what's the strategy? How do we get it done? We're still figuring out what needs or what's missing. But yeah, it looks like it should be doable. But again, still figuring out things.
That's really impressive.
So Vanchi, if you want to get your platform code up to upstream EDK2 platforms, Isaac and I would be happy to help with that.
Yeah, there's the fork was just put on GitHub. I'm sure. So the EDK2 team is actually working on, and yeah, your help is definitely appreciated.
All right.
Yeah, you're not the only one using IPv4. Sorry, I was just reacting to Sean's comment.
I can't remember IPv6 addresses even now, except for like : whatever. I can't remember that. Any questions? Does anybody? Don't worry, Christian. We're just cutting into my time, not yours.
Don't worry. I can make it quick. So yeah, let me first share my screen here. See if that works. All right. I guess it works. I hope you can see what's going on here. So what I'd like to show you today is the QA system that we built up over the last 2 years or so, or maybe 3 even now, which is actually attached to the Coreboot master branch. And what the QA system does is it does test every patch that gets submitted into the tree. So once it is in the tree, it does test the new master upstream branch if that still passes all the tests. So right now it's set up for Coreboot only, but basically that could be extended for every other firmware, more or less. So everything is public here, so you can just jump over to lava.9esec.io if you want to. I hope that's big enough to see that. Here, so basically what you get on the first side is a list of all the jobs that have been executed until we set it up, right? So we are at 27,000 now. And here you always see like a basic description of the job. So what is actually happening here now? Who was the submitter? Submit time and date, and some of these meta informations here. There are basically 2 different submitters. One is the Lava Health submitter, which is like a cron job that runs every couple hours to just see if the hardware we attach to the QA system is still okay. And there's the other submitter, Garrett. And as you might have assumed, Garrett is actually the one which is the Garrett system, so the Git system of Coreboot. When the patch gets submitted into the Coreboot tree, the build artifacts. So Coreboot actually has its own Jenkins, so its own build system attached to it. So every patch that gets uploaded and submitted into the Coreboot tree gets build tested, right? So Jenkins build it, and if the build runs through, everything's fine. These artifacts actually get then pushed to our QA system from the Jenkins on. And we do run these artifacts then on different types of hardware. So we do have basic tests for QMO, which is like a very basic setup. Most of the time we do test 3 things more or less. We have a basic payload, which is CBIOS. We stitch in and then just see if we can boot the board. We have an UFI, an EFI payload, which is Tiano Core here, and we have Linux boot as a payload, and then just see if we can KExec into one of the operating systems. We do also have real hardware attached, so QAMOS, of course, everything is virtualized. And we do also have real hardware attached here, which is the HP Compaq. That's like a small micro server. which is attached there. If you, so there are three symbols here. One is these bars, one is in the eye, and one is that fast forward sign. The bar itself gives you the job results, right? So here you see what jobs or what tests have been executed on the hardware, and how many passes and how many failed and how many were there in total. So this way you get like a quick overview if the passes that you run have been successful or not. You can have a detailed view on that job if you want to. That is actually quite verbose, right? What is happening under the hood is that we take the build artifacts which are coming from the Jenkins server, stitch like FSP and stuff into that binary to make it bootable on real hardware, and then we boot the hardware. The test itself has like various tags attached on it. So every hardware that we enter into that QA system has tags. For example, this hardware here has a hard disk, and it should run tests which have also the tag hard disk MBR. So we do legacy booting here and not some kind of EFI booting. Before the real test actually starts, the hardware gets provisioned. So that means we only want to test the firmware, right? So that means we want to rule out all other parts which are in the hardware to be failing, right? And this also means that we have to set up, every time we run a test, we set up a new fresh Linux system on the hard drive, which we later boot into and run our tests in. That means we have, for every hardware, we have a golden image, which does provision the hard drive with a Linux system, like with a Linux disk image. We can scroll through the log, so it's quite extensive. And maybe we can check out what's happening here, right? So here, actually, the QA system boots up the first time. And what you can observe here is that we're actually downloading the Fedora disk image here, and then we DD it on the hard drive. Once that is done, we do take the build artifacts that came from the Jenkins server and do boot the firmware again, or do boot the hardware again and see if that actually runs through, right? That is then actually happening here. So this is all the core boot output that gets produced while booting the hardware. And once we hit CBIOS, we do boot into the Linux kernel, which is a Fedora image. You see the full log of the Fedora image here. That's quite extensive. And then we hit the login shell, right? And these blue boxes in between are always like checkpoints of our tests, which the serial output actually has to reach, right? So at some point in time, we do, for example, expect here the login shell to pop up. These tests more or less have a timeout, right? So if nothing pops up after 5 minutes or so, that test is considered as a fail. And then every other subsequent test, for example, in this case, would not be executed, right? If that is successful, you get like a small info about that, and then we do run various tests on these hardware, right? So that is we do check something like LSPCI, LSCPU. We do some memory tests. We do check if the Ethernet interface came up correctly. We do also check, here you see LSCPU. We do also run some smoke tests, which are like some basic tests, if everything is fine, more or less. And also at the very bottom corner, at the bottom of the log, you do see ACPI firmware test suite tests that get executed here. And this actually executes like a numerous set of tests that have to pass so that this hardware, so that we consider this as valid here. So as I said, that is quite verbose. If you check, if you scroll through all the log, but that gives you all the information that you might need to debug the problem in the end, or if you see a regression coming up, so that the hardware behaves now differently from what you would expect. You can narrow it down to a couple of commits, and then you have a boot log in place to actually see what went wrong on the hardware, right? If you press that fast forward button here, it directly brings you to the end of the log. So that most likely actually brings you to the error if something went wrong. Right. So if that actually completes, so for every patch that gets submitted in the Kobo tree, we run various tests, at least 4 or 5 of these. So partially on QEMU and partially on real hardware. And if these succeed, we do post that to the Kobo Garrett with like a small comment, which more or less gives you says if all the tests passed or fail, right? Let me see if I can bring up one of these test message and see if that went through, right? So that you get an idea. So you see the QA system that actually made a comment here. So the patch has been submitted on November at 11 a.m. and more or less 5 hours later, our QA system actually attached these log here, right? And there you see how many tests passed, how many tests failed, and how many we did actually in total. You get the link to the detailed boot log or to the detailed test log, so to say, which gives you this test overview, what tests have been executed. And again, you can scroll in more on these things, see, okay, what test step does one of these tests really has? And that's basically it, right? Yep.
That's really neat. I might have missed it because there's so much to see. Do you have a test that would be able to look for performance regression, like I don't know, memory bandwidth or this? Like we had a problem on the Winterfell node. Jean-Marie remembers it well, where we had a disk bandwidth problem that we actually fixed in Linux, but we didn't even realize it was happening for a while.
No, so we do not have performance testing yet. I think we do boot up time tests, so how long the platform actually boots, but not real performance tests. But that is actually something that could be extended, right? So we are more or less just communicating over the serial console with the target. So you can then do whatever you want there.
Yeah.
So that is something that we most probably will add later on. For now, these platforms that have been added here are not like super high-class servers, right? We do have now a couple of OCP Delta Lakes here, which might be added also to that QA system, so that we get also a broader spectrum of test coverage, and maybe also something like performance test or load testing or so.
Neat. Yeah. It seems like it would fit in very well to your system.
Yeah.
Wow.
Maybe one thing I can show you still how that looks more or less under the hood, right? So that is actually the system that we built up. As I said, it's like 2 to 3 years development went into that. So on the very top left corner here, you have the Garrett and the Jenkins, which are basically outside of our QA system, which belong to Coreboot, right? The Jenkins itself, here you see the flow, pushes the artifacts onto an endpoint, an HTTP endpoint, where he just uploads them, right? We have a Lava QA client here, which periodically scans if new assets have been arrived here, and then we trigger the build, right? We do upload the Coreboot ROMs on our internal system, and then we trigger the Lava master server more or less to execute the test. depending on if that's QEMU or not, they run on a root server, virtualized, or they get forward to a Lava dispatcher, which is running on a Raspberry Pi, which does all the communication with the DUT here, right? All the results will be played back to the master, which actually then plays it back to the Lava QA client, which then actually gives feedback to the Garrett system. So that is how it all hangs together, more or less.
Yeah, in theory, we could definitely say we could put also the build process into our own system, but every project has its own, and it's there also different tests. So would it be a lot of work to reproduce them for all projects? But in theory, that's also possible. So we thought about that, but there's no clear decision yet if we are going to build stuff ourselves. Yeah, this is a long-term discussion, but I think it's probably easier at the moment to attach other projects like it is. So just
yeah, right. And also so a lot of firmware projects get built at least, or build tested at least, right? So why doing the job twice? If we can patch the artifacts that are coming out of the build system, that's no problem for us.
Yeah. Very cool.
I don't know again.
All right. Well, with any luck, let's see. I'm still visible. I didn't screw that up, right? With any luck, this will be short. What I thought I would, okay, share screen, share. What I thought I would do is, show the PC Engine's APU4, and I am hoping this time I've got a big enough font. So let's see how that goes. So the APU4 is core boot, and for people who want to develop this, I'll show you the reason I really liked APU4. And that partly comes back to because of the way core boot works. So I hit F10, and I hope it doesn't time out, but here's the set of choices I have about what to boot. iPXE, my USB drive, my built-in SSD. I've got Nerf, which is Linux boot and uroot built into the flash itself, and I've got my payload for setup. And what's awesome about this is very, very simple to change. So I'm going to go ahead and pick Nerf. You can tell how old this image is because it's still called Nerf. And now we're booting, of course, the kernel. And I am going to try fly without a wire here. So this is now up as a CPU server. And here comes the flying without a wire part. This is another board that is supported in the mainboards repo. And so before I actually, burn a new CPU kernel into it, I might want to test that CPU kernel. But first, I'm gonna do one thing to make sure I've got it. Okay, so I'm gonna actually go ahead and use the internal program mode and on flash ROM. And well, that was weird. Yeah, demos always fail, right? See if that'll work. Yeah, okay. All right, fine. Be that way. I don't know. Oh, I'm being a dummy, that's fine. I want to read it, which I'm doing. Right, and notice my command here was CPUA flash ROM p internal -r xyz.rom. And there's a little bit of a fun trick to this in a second if it works, which anytime there's a demo, you take a risk, right? Okay, so notice that because I'm running CPU, when I did the write, it ends up right here in my home directory on the machine I'm on. I don't have to SCP it back because it's the CPU command. That's actually not the real reason I did this. For anybody who's used an EFI firmware volume, you know how complex it is. This is the core boot Cbfs. and you can see this is dead simple. So you can see the parts in this that are for the AMD part, which is of course the APU. Here's the Giza. Here's the Pixie ROM that it uses if you boot with Pixie. And then here's the RAM stage. And then where is my NERF image? Somewhere in here there should be, image NERF. So that's my 3 megabyte image. That is the Linux boot and uroot piece. So what I find really nice about this is, as the APU4 is a way to develop, is that I can have so many different things that I boot from, and it's so easy to get to them just with that Shift F10. And in the default mode, it just net boots. So that's a Linux boot. I mean, an OSF compatible node. And let's go ahead, since I've failed at this once already. Let's see if it works this time. So here it is. We're starting a new kernel, which should be a functional CPU kernel for this device, right? And let's see what we get. I actually tried this earlier today and it didn't work. That's why I'm wondering. And then we're waiting for the usual timeout. The slowest part of any boot is dealing with the disk, right? So this is up. I can't tell if it got an IP address, so let's see if I can even ping it. So there's some problem. Unfortunately, I've broken this kernel at some point, but the built-in kernel still works. So it's easy to kind of repair the broken kernel, because all I've got to do is restart the machine and I continue to kexec and see what I did wrong. That's about all there is to that demo. I mainly wanted to quick do this, and if anybody has questions, then I can answer them, and otherwise we can get an earlier lunch. So earlier lunch is always a good thing, right? And that used IPv4. So that's our third machine to use IPv4 today, and our third machine to use the mainboard repo. So we must be doing something right. That's kind of it. So unless there are questions, we are done for the day. Or this part of the session, I should say. All right, Ryan, back to you.
Oh, wait, I was actually wondering, why is everything, oh, not anymore, but everything was printed twice.
Early print K, I always leave it on keep when I know I don't need to use it, just in case. It's just a built. Yeah, for anybody who's familiar with early print K, I tend to leave keep enabled, because sometimes when the console goes south is the one time you wanted to know. So I would advise that. And anyway, that, if you don't think you're really going to use your console, then just leave it on keep. And then if the regular Linux console goes south, you've still got something. Just a habit of mine for development.
That sounds good. Okay, I guess this would be a good time to break for lunch. I don't see any new questions. Yeah, so I guess this is a good time to break for lunch. Ron, maybe we could have another one of those breakout sessions. We're returning at 1:25.